Good evening, everyone.
Good evening, sir.
Now we are starting. Okay, so welcome to the class of Introduction to Complex Biological Systems. We will be starting with the week 4 lecture. So those who don't know me, I am Srijan Sen from IIT Kharagpur, and I will be taking the live session of week 4 of that particular course. Right. So I'm sharing my slides with you all. Do you have any questions from the last class, something like that? Any doubts from the last class? Any difficulties in any assignment questions, things like that? Anyone? Anything? So, no doubts? Okay. So, we should start. So, today's class is mostly on enzymes. So, last class we talked about proteins and the different types of how proteins are formed, then what are the functions of proteins, things like that, the biological importance of proteins. Uh, Okay. So today's class is mostly about one such type of a protein, that is enzymes, known as also known as the biological catalyst. Why do we call them? We will get to know as we move ahead. So starting with, we will be going with first the classification and mechanism of enzymes. So in general, enzymes are proteins that increase the rate of a reaction by lowering the energy of activation. They catalyzed nearly all chemical reactions that takes place in the cells of body. And the good thing about it is that it is neither altered or consumed during a reaction, which is a significant characteristic of catalysts. And these are quite reusable. So we need to understand the difference and the similarities which the chemical catalysts share with the biological catalysts, also known as the enzyme. So you will find that there are certain shared properties, one of which is that enzymes are neither consumed nor produced during the course of a reaction. At the same time, enzymes do not cause the reaction to take place. They are mostly involved in decreasing the activation energy that is required for carrying out a particular reaction, which is very similar between that of a chemical catalyst and the enzymes. However, you would see that obviously it's a biological catalyst, so it should have certain differences that also occurs with the chemical catalyst. One of which is that enzymes are proteins, they are biological catalysts, and they take place mostly inside the cells, or they take place in vitro, whereas chemical substances have to be provided from outside, things like that, right? So enzymes are mostly highly specific and produce only the expected product from the given reactants or the substrates. Now, enzymes may show a high specificity towards one substrate and exhibit a broad specificity using more than one substrate. So, enzymes usually functions with a moderate pH and temperature range, whereas the chemical catalyst do not require any of certain things. Now, how a catalyst works, we generally know. It's very similar to how the enzymes works. It's mostly important for decreasing the high energy barrier or reducing the activation energy, if we have to talk in a scientific term. So you see that there are multiple frogs that cannot cross the energy barrier because of the high barrier. So catalysts are mostly used for lowering this energy barrier. They do not have to do anything with the reactant or the product. They are mostly playing a role in reducing the activation energy that is playing a significant role in the catalytic process or in the occurrence of a reaction. Now, the concept of free energy is more or less like it's mostly understood by the concept of the Gibbs free energy. So, more free energy means less stable, greater work capacity. And when there is more free energy, less stable, greater work capacity, it means that the reaction will not take place. That means you can understand that the delta G is greater than 0, which means it's not a spontaneous process. On the other hand, when delta G, that is the change in the Gibbs free energy, is less than 0, it's a spontaneous process, that is less free energy, more stable, and less work capacity required for carrying out a particular reaction. We understand these particular concepts. Now, when the free energy of a reactant is greater than that of a product, you will see the free energy changing for the reaction is also negative and the reaction occurs spontaneously, like you observe in figure A. For figure B, what you see that the reactants and the reactants are at a much lower energy compared to that of the products, and the delta G reaction, which is mainly product minus reactants, is positive value. It means that the reverse reaction can be possible, that is conversion from a product to a reactant, but the forward reaction is not feasible or spontaneous. Now, the components of enzymes are very important to understand, one of which is the apoenzyme. Apoenzyme is the protein portion of the enzyme which is inactive, and it has or it requires certain cofactors, which is the non-protein portion or the activator of the particular apoenzyme. Now, these cofactors mostly includes your essential ions or coenzymes. Like essential ions in the sense, sometimes you require divalent cations, metal ions like the metalloenzymes. Even you would see that there are certain like hemoglobin even requires metal ion for its activity, things like that. Or you have some activator ions which are loosely bound. So these are certain essential ions which requires for the activation. Now, there are certain enzymes like cyclization enzymes. You have sortase that requires calcium for its activity. Now, the other part are the coenzymes that includes the co-substrates which binds loosely and the prosthetic groups which binds tightly to the apoenzyme. So, in general, apoenzyme is that protein part which is inactive without the cofactor. Cofactor can be the coenzyme as well, let us consider, and the apoenzyme along with the cofactor or the coenzyme, whatever you say, forms the holoenzyme. Now, this holoenzyme means the whole enzyme, the active part of the enzyme which is capable of binding to the substrate. Right? Now, the area of the enzyme where the substrates bind or attaches is called the active site. It can be very different from the catalytic site, or it can be same as that of the catalytic site. But binding site holds the substrate in place. Catalytic site is where the reaction occurs. For most of the enzymes, the binding site may be the catalytic site and the active site, but it is not always important that the catalytic site is same as the binding site. Okay, now to understand this, the substrate enters the active site of the enzyme. It can be like whether it directly fits into the enzyme or it's a, so it can happen in two ways. One is the lock and key model, like if the substrate can directly fit into the active site of the enzyme, the activity happens, or can be an induced fit model where the enzymes do not have that particular orientation to hold up that particular substrate. What it does, it changes its orientation and it captures the substrate to carry out a particular reaction. So what happens, the substrate binds to the active site of an enzyme, then the reaction takes place, it lowers the reaction happens, the product formation happens in the bound state to that enzyme, and then the products leave. The enzyme is not hampered, the enzyme is not changing the reactant or the product. What it's simply doing is basically carrying out the particular reaction. Now, like I was speaking, there are certain theories behind how the substrate binds to this enzyme. So one is the lock and key model. So the active site, in this model, the active site has a rigid shape. Only the substrates that fits the shape of this active site can only come and sit over there and carry out its activity. Now, but this is a very older model. However, it does not work for all the enzymes, even though it's very specific, because only certain substrates can come and sit in that active site and carry out a reaction. So these enzymes are very specific in nature. However, if you need certain enzymes, a wide range of enzymes, like normally enzymes should be in certain manner, like it can carry out multiple types of the reaction at the same time. So one enzyme helping, like you have certain proteases that can cleave multiple proteins, because it is specific towards a particular maybe sequence, or it is specific towards a particular amino acid, things like that, like the serine proteases as an example. So it might not be the entire protein has to, you have to take into consideration. So there comes the next theory, which is the induced fit model, where the active site orientation and the structure of that particular enzyme changes a bit. Rather, the orientation of the active site changes a bit. So it's flexible, not that rigid. Fine. So the shape of the enzyme, the active site, and the substrates adjust to maximize the fit, to improve the catalysis. If the substrate does not bind properly, if the active site is not able to function properly, what happens? The reaction rate slows down, and it's same as that for a normal reaction. Then you don't require the need of enzymes. And this model is more consistent with the wide range of enzymes. Now this is the IUB nomenclature, which for the time being you may not remember, just I'm telling because you need to understand the enzyme classification. So there is a 4-digit code. The first digit is signifies the major class, that is 1. Then what you have 9 is basically the subclass. The third digit, that is 5 over here, indicates the sub of the subclass, and the final digit is basically it represents a specific enzyme. So for example, if it's 2.7.1.1, that indicates glucose phosphotransferase for it. So 2 is the class name, that is transferase. 7 is the phosphotransferase, that's the subclass name. The third one is subclass, that it takes the hydroxyl group as an acceptor, and the other one is a specific enzyme, that's D-glucose as the phosphoryl group acceptor. So these are the significance of the 4 digits that you have in the IUB nomenclature. Now, the classification of enzymes are entirely based on like into 7 categories, starting with oxidoreductases, transferases, hydrolases, lysases, isomerase, ligases, and the translocases. Fine. Now, over here, there is a very important term which you need to basically understand. One is the one is the catalytic efficiency and the turnover number. So they go hand in hand. So how is it so? So mostly enzyme catalyzed reactions are highly efficient, proceeding from like 1000 to 10 to the power 8 times faster than that of an uncatalyzed reaction. Right now, each enzyme molecule is capable of transforming 100 to 1000 substrate molecules into product each second. Now, the number of molecules of substrate converted to product per enzyme molecule per second is known as that of the turnover number. So, higher turnover number means it is being able to, so the number of molecules that the enzyme, that one enzyme is converting to the product per second is basically more. That means it has a higher turnover number, and turnover number in that sense is a value. It does not tell you about anything. So turnover, higher turnover number means the catalytic efficiency of that particular enzyme is higher. Now, so like you understand that the enzymes are classified into like 7 different classes. So we will go with the oxidoreductase. You know what oxidoreductase do. Now these enzymes catalyze oxidation and reduction reactions like You have heard of the pyruvate dehydrogenase, which catalyzes the oxidation of pyruvate to acetyl coenzyme A. Then you have alcohol dehydrogenase, lactate dehydrogenase, cytochrome oxidase, things like that. Now the next one is transferases. So transferases catalyze the transfer of a functional group, like maybe you have a methyl group or an acyl group, amino phosphate group from one molecule, that's the donor, to another molecule, which is an acceptor, like the kinases. Now hydrolysis, what they do, they catalyze the hydrolysis of various bonds like ester, ether, peptide bonds, glycosidic bonds, CC bonds, CX bonds, C halides, then phosphate nitrogen bonds using the role of water. What do lyses do? Lyses catalyze the cleavage of various bonds by means other than hydrolysis or oxidation, often forming a new double bond or a new ring-like structure. Isomerases, you know that it's responsible for catalyzing the rearrangement of atoms within a molecule to form an isomer. Okay. Then the ligases, mostly what they do, they catalyze the joining of two large molecules by forming a new chemical bond, typically with a simultaneous hydrolysis of ATP, adenosine triphosphate IDP interconversion. And finally, we have the translocases. So translocases catalyze the movement of ions or molecules across biological membranes, such as like inner mitochondrial membrane. So these are the 7 different classifications of that. But these enzymes need to work at a optimal temperature and optimal pH. Why is it so? Because it's the temperature and the pH both are dependent on any biological in a biological context. So like some enzymes work at a higher temperature, some enzymes work at quite a lower temperature. The stability of the enzymes also matter. So things like that. So there are certain enzymes that works at body temperature. You will find these enzymes working in our body. Also the pH effects, because you know that there are certain enzymes like pepsin which works at a lower pH. Then you have trypsin that mostly functions in an alkaline range, and then you have the human amylase enzyme that functions at a neutral pH or a body pH. So these are quite of the basic things about enzymes. And then you have certain substrate concentration and the reaction rate that is quite required for the understanding of enzymes. Like the rate of a reaction increases as the substrate concentration increases. Then maximum activity occurs when the substrate in the enzyme is saturated. That when all the enzymes are binding the substrate. Then comes the catalytic power. So catalytic power is defined as the ratio of the enzyme catalyzed rate of a reaction to the uncatalyzed rate. You can find some examples and the constant rates over here. Specificity. This is a very important characteristic of enzymes because it needs to be understood what the substrate is going and binding to. It is not that all the enzymes can bind multiple substrate. That does not make a sense. If you can open a lock with a multiple key, that does not make any sense to that particular lock. It's similarly like that. So specificity is very important. The enzyme is specific to a particular substrate molecule. So the substances upon which an enzyme acts is called a substrate. The selective qualities of an enzyme are recognized as specificity, and specific site on the enzyme where the substrate binds and the catalysis occurs is called the active site. And enzymes have different roles in regulation. So regulation of enzyme activity ensures that the rate of the metabolic reactions is appropriate to certain cellular conditions. It's essential for the integration and regulation of metabolism, and it's achieved by various ways: the inhibitor, activator, hormonal, and rate of synthesis. So in terms of specificity, the enzyme should be highly specific compared to other available catalysts. It should catalyze only specific reactions, like it can be stereospecific, optical specificity, reaction specificity, substrate specificity, but it should be specific. Like it can maybe catalyze a L isomer, not a D isomer. Maybe it can catalyze you can say breaking of water molecule, but not breaking of an ammonia molecule, right? So things like that. So optical specificity is able to recognize the optical isomers, like I was telling, the DL, the L amino oxidases. So isomerase do not exhibit stereospecificity because isomerism is just you are changing one molecule to the other. So if it's uh, stereo specific, what would happen? It will be able to identify maybe an alcohol, but not an uh, ester, which is a product of that, or maybe even an um, aldehyde or a ketone. Okay. Now, reaction specificity is that amino acids can undergo deamination, transamination, decarboxylation, and each should be catalyzed by a separate separate enzyme. So, it can catalyze one specific reaction over the substrate. Cool. Okay. Now, substrate specificity is that it should be specific towards the substrates like the glucokinase, the galactokinase, and both transfer phosphoryl groups from the ATP to the different molecules. Like there can be like three types: absolute substrate specificity, relative substrate specificity, and the broad substrate specificity. So absolute substrate specificity means it should act on only one substrate, like the urease. Relative means like it should act on structurally related substrates, and like it can be group dependent or bond specific. Like group dependent means like it can act on specific groups like trypsin break peptide bonds between lysine and arginine. Chymotrypsin acts on aromatic amino acids. And bond specificity means it should act on specific bonds like the proteolytic enzyme and the glycosidase. And the broad specificity is like it can act on closely related substrates like the hexokinase acts on many hexoses. Okay. Now, the chemical nature and properties of enzymes, it can be protein or RNA, and then if it's an RNA, it can be translated to a protein. The tertiary structure and specific conformation is essential for the catalytic power of an enzyme. Hollow enzyme should be a functional unit, which is a collaboration of coenzyme and the coenzyme. Now, prosthetic groups and coenzyme or cofactors. So, prosthetic groups are basically non-protein molecules. Even coenzymes are non-protein molecules. Prosthetic groups are tightly bound. Coenzymes are loosely bound. Prosthetic groups have a stable incorporation. Coenzymes are dissociable. And prosthetic groups cannot be dissociated because they are tightly bound, and coenzymes can be separable by dialysis because these are small molecules. Okay. Yeah, so this is about the basics. Now we would be getting into enzyme kinetics and enzyme inhibition. If you have any questions up till this part, you can ask me. So this is just about enzyme classification and things like that. How an enzyme functions, what an enzyme does, what are the different types of enzymes, what does each of these enzymes do, and the different terms that are associated with this enzymes. So once when you are able to capture all of that, we will be going into the most important part. That's the kinetics and the inhibition. Maybe I will give 2 minutes. If you have any questions, you can. So we can go with the enzyme kinetics then. Great. Okay. So enzymes mostly follow zero order kinetics when the substrate concentration is high. So zero order kinetic means that there is no increase in the rate of a reaction when more substrate is added. Now the Michaelis-Menten equation is very important. So it's basically understood as E plus S, where E is the enzyme, S is the substrate, and then K1, K2, K3, K4 are all the rate constants that are associated with it. Then you have ES and E and P. Okay. So what will be the rate of ES formation? That is K1 of ET minus ES into the substrate concentration, where ET is the total concentration of the enzyme and K4 is considered negligible because it's not coming back from the product to the previous state. Now the steady state approximation tells, like, if you have a intermediate or a transient state that is getting converted to the product, and that particular step cannot be captured or cannot be isolated separately, the rate of that particular state becomes zero. So you understand that why when d of ES, concentration of ES by dt is basically zero. So that means K1 of this particular thing is equal to K3 into ES plus K2 into ES. Now, for this equation is basis of for the final Michaelis-Menten following algebraic rearrangement and substitution of Km and Vmax terms. So Michaelis constant or Km, so the substrate concentration that produces half the maximal velocity, that is Vmax by 2, is called the Michaelis constant. So what is the significance of this? So Michaelis constants have been determined in many commonly used enzymes. So the size of Km tells us everything about a particular enzyme. What are the things? A small Km indicates that the enzyme requires small amount of substrate to become saturated. Hence the maximum velocity is reached at relatively low substrate concentrations. A large Km indicates the need of high substrate concentrations to achieve maximum reaction velocity. Now the substrate with the lowest Km upon which the enzyme acts as a catalyst is frequently assumed to be enzyme's natural substrate. This is not true for all enzymes. And a Km of 10 to the power minus 7 molar indicates that the substrate has greater affinity for the enzyme than that of Km, which is 10 to the power minus 5 molar. So lower Km means the substrate has greater affinity. Now, the significance of Km is that it's an enzyme kinetic constant. It indicates that the substrate concentration required for the enzyme to work efficiently. Low Km indicates high affinity of the enzyme towards the substrate and vice versa. And Km is required when enzymes are used as drugs, and if in use of enzymes in immunodiagnostics requires the Km of enzymes. A more specific term is basically Kcat. So at high concentration of substrate, the overall velocity of the reaction is Vmax, and the rate is determined by the enzyme concentration. So the rate constant observed under these conditions is called the catalytic constant, which is defined as Vmax equals to Kcat into E total. That's the total enzyme. And Kcat is Vmax by E total. So Kcat, we know, is the maximum number of substrate molecules converted to product each second by each enzyme or each active site. So the catalytic constant measures how fast a given enzyme can catalyze a specific reaction. So based on the assumption of equilibrium, we can come to this equation that if K minus 1 or the reverse kinetics is very, very high than K2, we can write it as Ks, which is the dissociation constant of the ES complex, using this particular formula. And we know from the steady state approximation that D of this is equal to 0, because by the time it's producing, it's also getting used up for the formation of the product. So the rate is basically 0 over here, because the rate of change is basically 0. So we write all of these certain equations where the total enzyme concentration is the total of the enzyme concentration and the enzyme substrate complex. So combining this equation, we can rearrange it and write it as this, after which we rearrange it and do certain divisions, rearrangement, multiplication, and we write it as concentration of enzyme substrate is equal to the total enzyme concentration into substrate concentration divided by Km plus substrate concentration. So Km is equal to K minus 1 plus K2 by K1. And if we write it like this, then the equation becomes V naught, which is equal to the rate of the product formation, is equal to K2 Es is equal to whatever the equation was over here. So we are writing it in this way, only that we are adding the K2 over here. Now after this, so when Vmax is basically V naught is Vmax by 2, what happens? So Vmax by 2 equals to Vmax into substrate concentration by Km into S. You will see that Km is equal to the substrate concentration. So that is how we explain Km. When the Vmax is exactly half of V naught, we write it as V naught is Vmax by 2, then Km becomes equal to the substrate concentration. So Vmax is equal to K2 into the total enzyme concentration. And this is a very important equation where V naught, which is the initial velocity when the reaction has just started, is equal to Vmax into substrate concentration divided by Km plus substrate concentration. Now when we plot Vmax versus substrate concentration, we get a curve like this, where Vmax V naught, when it is Vmax by 2, that is the point of Km. So Km equals to substrate concentration, where V naught is half of Vmax. So the Km varies widely among the different enzymes that we obviously expect. So as the Ks decreases, the affinity for the substrate increases. So the Km can be a measure for the substrate affinity. Like we have Kd, which is the dissociation constant, Ka, which is the association constant. So lower the Kd value, higher is the affinity. Higher the Ka value, higher is the affinity. So similarly, Km, lower K or lower Ks means higher affinity. So the factors that basically affect the enzyme kinetics is there are different things: enzyme concentration, temperature, pH, substrate concentration, inhibitors, then you have product concentration, activators, physical agents, things like that. Now substrate concentration, it basically is indicated by a rectangular hyperbola, the initial velocity when the little substrate has reacted. The reasons for the three curves, three phases of a curve is, in the first phase you see that the substrate concentration is low and most of the enzyme is free and unreacted, so therefore the velocity is proportional to the substrate concentration, indicating a first order kinetics, because when you are adding more substrate it is reacting. Now you reach a phase where it is a second phase, that's half of the enzyme molecules have reacted to it and the velocity is not directly proportional to the substrate concentration. At this stage the enzymatic reaction shows a mixed kinetics, that is a first order and zero order kinetics. And now you have reached a stage where even when you are adding more and more amount of substrate, there is no change because the enzyme is no longer free to react, and this is a zero order kinetics. Now based on this you can plot, like previously we plotted V naught versus substrate concentration. Here we are plotting 1 by V naught versus 1 by S. This is a double reciprocal plot. You have, it's the same equation, you're writing it in a different manner. You get a straight line curve where the x-intercept is minus 1 by Km, the y-intercept is 1 by Vmax, and the slope is Km by Vmax. So if you know the substrate concentration, you can find the Km from the x-intercept, you can find the Vmax from the y-intercept, things like that. So Lineweaver-Burk's plot gives you a slope of Km by Vmax. So 1 by V naught is equal to 1 by Vmax if it's extrapolated along the x-intercept. So turnover number, you know, kcat is how many reactions an enzyme can catalyze per second, and that's the turnover number, the explanation of a catalytic efficiency. Now for Michaelis-Menten kinetics, K2 is equivalent to Kcat. Why is it so? Because the K2 is the rate determining step over here. And when S is very, very less than Km, that's very little enzyme substrate concentration is formed, then the equation becomes V naught is quite equal to Kcat by Km into enzyme concentration and the substrate concentration. And Kcat by Km is the measure of the catalytic efficiency and is reported whenever you are reporting some novel enzymes. But somewhere or the other, the kinetics needs some kinds of inhibition or inhibition occurs. So there are three types of inhibition that can happen: competitive, mixed and uncompetitive. Competitive means that where the inhibitor competes with the substrate. So even the inhibitor has good binding to the enzyme compared to that of the substrate. So when the inhibitor binds, it's Ki and there is no reaction. When the substrate binds, you get the product in the enzyme. So the equation becomes Ki equals to enzyme into inhibitor by the complex, and then there is another factor because Km that was mostly allotted for substrate has to be now allotted for the inhibitor, and you get an alpha Km. So what is alpha? Alpha is 1 plus inhibitor concentration by the constant. That is the Ki controlling it. So you see over here now, without the presence of any inhibitor, alpha is 1. So with increasing, so you see that with an increasing V naught and an increasing substrate concentration, when alpha is 1, that is no inhibitor, you get a curve like this. Now with increasing concentration of the inhibitor, you see that alpha value also increases. So if alpha value increases, somewhere you see the curve straightening a bit. And upon getting into the double reciprocal plot, where you are plotting 1 by V naught versus 1 by S substrate concentration, you see that upon A alpha, which increases, the x-intercept shifts towards the origin. The 1 by V max remains the same and the slope increases. For an uncompetitive inhibition, where both there is no competition, but in the presence of the substrate also the enzyme can the inhibitor can bind because it's binding in a different site apart from the substrate binding site. Even then there is no reaction, and there you will see that even the Vmax decreases, the alpha the Km value decreases, and the slope remains the same. For a mixed type of an inhibition, what happens? You basically observe that the intercept is shifting a bit. It depends on what will be the alpha and the alpha dash in that perspective. So you will see the Vmax also changing, the Kmax also changing, as well as with an increasing I, the slope increases. But it's entirely dependent on the alpha and the alpha dash value, which is mostly for the determined by the reaction rate of whether it is binding in the first step to the enzyme or whether it is binding along with the substrate. But even for a mixed or an uncompetitive inhibition, the substrate binding site is different from the site of inhibition. So these are some equations. You need not remember them as of now. What you need to know is basically this particular graph, this particular chart, where if there is no inhibition, Vmax, apparent Vmax is Vmax and apparent Km is Km. When it's a competitive, Vmax remains Vmax. Vmax does not change. Km increases. For an uncompetitive one, Vmax and Km both decreases. For a mixed one, Vmax decreases and Km apparent remains more or less the same if alpha equals to alpha dash. If they are different, it might increase, might decrease, but it might have a change if alpha and alpha dash are not the same. Okay, So yeah, that's all about the enzyme kinetics and the inhibition part. If you have any questions, you can ask me on this portion. Next, we will go into the quiz time or the question and answers. Okay, then we should go to the quizzes. So it's now over to you people who would be answering me. Okay. So let's get to this one. Enzyme velocity can diminish over time due to decrease in substrate concentration, product inhibition, pH changes, thermal inactivation. What is your answer? Those who are present, everyone try to give an answer. I see I don't know how many of you are there. Like one, two, three, four, five, almost five, six people are there. So yeah, try to give an answer. It's nothing that if you're wrong, it's problem. It's fine. So enzyme velocity can diminish over what of the reasons? So as the reaction proceeds, you will see that the substrate is consumed. So there can be a decrease in the substrate concentration. Now sometimes the accumulation of the products can bind to the enzyme and inhibits its activity. So that is possible. pH changes definitely affect it, and thermal inactivation also affects the enzyme velocity. So 1, 2, 3, and 4, which is option C. Now the next one. You see the reaction shows represents the formation of an enzyme substrate complex followed by the breakdown of ES and the release of product. So what will be the rate of ES breakdown? I have got one answer. Where are others? Others try to answer. Yes, this equation was discussed. So yes, it is option A. K minus 1 into the concentration of this enzyme substrate complex plus K2 of the enzyme substrate complex. Yes, option A is correct. The next one, in a mixed inhibition, the enzyme inhibitor complex EI has a dash affinity for dash compared to that of dash. So over here, C, D both can be correct. Lower affinity for the substrate compared to enzyme, or higher affinity for the enzyme compared to the substrate. So C and D both can be correct over here, whichever you give right. Now the next one says deviation from Michaelis-Menten kinetics occurs when. So when does deviation from Michaelis-Menten occur? So I've got one answer. So Michaelis-Menten is basically based on a single substrate. Enzymes with multiple substrate will require there will be more complex reactions. Then the substrate binding is irreversible. So the model basically assumes a reversible reaction, and the breakdown of ES to the enzyme and the product is a rate limiting step. So irreversible binding would violate this particular assumption. So we have got 1, 2, K3 is uh, so KCAT. So this does not have anything to do with the deviation. Cooperativity. So cooperativity would actually make the equation more sigmoidal, not an hyperbolic one. So that would also lead to the deviation. So 1, 2, and 4, both are 1, 2, and 4. So that is option C, which is correct. Yeah, I've got correct answers. That is good. Next one, in competitive inhibition, an inhibitor binds. This is quite easy. When enzyme at a site other than the active site, only to the substrate, reversibly at the active site, covalently to the ES complex. Where does the inhibitor bind in a competitive inhibition? So basically, competitive inhibition is a type of an inhibition where the inhibitor that is quite structurally similar to that of the enzyme is binding to the active site. So when the inhibitor is bound to the active site, where the substrate was supposed to bind, everything gets problematic. So it binds reversibly to at the active site. Okay. So option C, yes, option C is correct. Now this one shows what type of an inhibition: competitive, uncompetitive, non-competitive, or mixed. So what type of an inhibition is shown over here? Where you see that there can be a substrate concentration. No, A is not correct, because just I discussed competitive inhibition means it should bind to the position where the substrate is also binding. But here you see the substrate binding site is very different from that of the inhibition binding site. This is an example of a non-competitive inhibition because the inhibitor binds to the site on the enzyme that is different from that of the active site, and this binding occurs even whether the substrate is bound or does not bound. It does not matter, it just goes and binds and inhibits the reaction. So it's a non-competitive inhibition. Okay, now let's get into quite simpler things. The site where the catalytic activity of the enzyme generally takes place. So let's try this too. Where does the catalytic activity of an enzyme take place? Okay, I've got one answer. Um, B, active site. Yes, that's the active site. That's correct. It's the active site. The next one is the reaction S to P is negative in the direction of S to P. So reaction equilibrium will favor the formation of which substance? Is it P or S? So from S to P, the um, delta G naught is negative. So that means which one of the product will be formed? Is it P or S? So what does negative gives free energy indicate? These are easy questions. You people were giving quick answers to tough questions. But these are basically very easy questions. So delta G naught is negative. What does it mean? It means that the reaction is spontaneous, and it's spontaneous towards the forward direction, that is S to P. So this means that the formation of the product will be more. So option A. Okay, right. Now for the reaction S plus E to whatever, there are some middle steps, and then E plus P, the quantities can be, which of the quantities can be measured experimentally? So which of these quantities can you measure experimentally? Substrate, product, total enzyme, bound substrate, bound product, bound enzyme, free product. Which of these can you measure experimentally? So you can measure the total enzyme because that is what you're adding from outside. There are different ways of how you can measure it. Also, the substrate concentration and the product concentration can be measured with time using multiple enzymatic assays that are present. So option E is correct. Fine. The next one says which of the following determines substrate specificity of an enzyme? Complementary geometry, complementary electrostatics, degree of hydrophobicity or hydrophilicity. So which should be the ideal for determining the substrate specificity of an enzyme? Yes, complementary geometry of the substrate and the enzyme is basically the dominating factor over here. right? So option A is correct. Okay, sure. Right. So while monitoring the activity of an enzyme in UV spectrometer, which two parameters are monitored in the instrument and in which axis? So what do you have in the x-axis and what do you have in the y-axis? So basically we have we always have absorbance in the y-axis. I would have been very happy if I would have got wavelength in the x-axis, but that's fine. Even okay, so you're measuring the activity of the enzyme. So time in the x-axis. So time will be there in the x-axis and absorbance will be in the y-axis. So option D. Next, a rate versus pH curve with an inflection point at pH 4 suggests the involvement of a or an dash in the catalytic step. Hydrophobic, hydroph- hydrophobic amino acid, acidic, basic, or metal ion. So if you're having an inflection point at pH 4, it means that there is an acidic amino acid that is playing a role because the pK is towards an acidic site. So anyways, the inflection point would be towards a acidic pH only. So it's an acidic amino acid that's playing a role. That's option B. Okay. Now you have to choose the incorrect statement or statements about the multi-step reaction. So which of the statements are incorrect? So statement 1 says the free energy of the intermediate must be greater than the transition state. This is incorrect because the free energy is the local of an intermediate is basically the local minimum of the reaction coordinate, while the free energy of the transition state is the local maximum. Therefore, the free energy of transition must always be greater than the intermediate. So that is incorrect. Statement 2 is correct. Statement 3 is saying the free energy of an intermediate may be greater than that of the reactant. Possible. Correct. The 4 says by catalyzing the reaction, the enzyme must decrease the free energy of the intermediate. We all know that's incorrect because it's supposed to. Okay, so they do not actually decrease the free energy of the intermediate. They decrease the free energy of the overall reaction. That is why it is incorrect. It's not the intermediate specifically. So that is why this is also incorrect. So 1 and 4, that is option D. This one, okay. Right. So the enzyme active site should preferably be more analogous to product, substrate or the transition state. No. The active site should be analogous to the substrate always. If it does not bind the substrate, what is the point? Even if the transition state is fitting into the active site, makes no sense. The substrate has to go and bind, right? So it's the substrate only. That's option 2. Let's see. Let's go over here. Let's get into quite these things. Okay. So which of the following is not true for an isozyme? So what are isozymes? So those who are not aware of what are isozymes, so they have the same Km values. So they are different forms of the enzyme that catalyze the same reaction but differ in their amino acid sequences, as well as differ in physical and chemical properties and kinetic characteristics. And this allows for the different regulation and the function in different tissues or developmental stages. Okay, so therefore that they have the same Km values is basically incorrect. So that is not true for an isoenzyme. So option B is the incorrect one. Okay. Then the next one says when a product accumulates in a cell, optimal amount its production is decreased by the inhibition of an enzyme involved in its synthesis. So then a product has been utilized, blah blah blah, and then this inhibition is a mechanism by which the concentration of certain cell constituents is limited. So what type of inhibition is this? So what sort of inhibition is basically happening over here? Very good. It's a feedback inhibition because whatever you are seeing over here, so it's like a switch on, switch off system where the end product inhibits it and then it goes back and tells, no, I require it for maintaining the homeostasis and stuffs like that. So I need the formation of the product to continue the formation of the product. So yes, that's a feedback inhibition. Okay. Um, these are the certain things which you can try it. Okay. In Michaelis-Menten kinetics, Km is defined as, what is Km? Very simple. Yes. So the concentration of the substrate required to reach half of the maximum velocity. So Km equals to Vmax by 2, and at that where V naught equals to Vmax by 2, it is the substrate concentration. So Km equals to substrate concentration when V naught equals to Vmax by 2. Okay, try the next one. Advantage of using Lineweaver-Burke plot. Okay, it linearizes the Michaelis-Menten equation, that is correct. It's easier to extrapolate a straight line, that is also correct. The errors in Km and Vmax are small. Uh, and the important parameters can be determined from the intercept in two axes. So I just did not mention it's an MSQ, but anyways, all the four options over here are correct. Right, and the last question for the day: which among the following statements is or are true? So you read the statements and tell which of the following are true. So acetyl cholinesterase is hydrolyzing the neurotransmitter acetylcholine in the synapses and terminates its activity, and it acts as a non-competitive or um, irreversible inhibitor. This is false because this enzyme is hydrolyzing the acetylcholine in the synapse to terminate its activity. However, it's not a competitive inhibitor. However, it acts as a competitive inhibitor, not a non-competitive or an irreversible one. So this is incorrect. One is not right. So you can eliminate option A and D. So you have 3, 4 and 2, 4. So let's see what is 4. So there are 2 lysine residues and 1 histidine residue in the active site of ribonuclease A. That is also wrong because the active site of ribonuclease A contains 2 histidines, histidine 12 and if I'm not wrong 119, and 1 lysine residue in the 41st position. That is crucial for its catalytic activity. So 4 is also incorrect. Okay, 1 is not just okay. 2 says due to pyruvate kinase deficiency, hemolytic and anemia is observed. That is correct. Both M-type and L-type isozymes of pyruvate kinase are allosterically regulated. That is also correct. So 2 and 3 are correct. So one which says it acts as a non-competitive and irreversible inhibitor, I guess that is also correct. Okay, so because sometimes it happens that it might act as a non-competitive or an irreversible inhibitor, but generally it happens to be like a competitive inhibitor. So I was just checking that only. So yeah, it's possible to that it might act as a non-competitive and irreversible inhibitor. So option A is basically correct, which is 1, 2, and 3 are correct over here. Okay, yeah, that's all. If you have any questions, you can ask me. Else, we are done for the day. No more questions? Then thank you. We will again meet in the next week.